Welcome back. This is Larry Benko, W0QE. And this video is about harmonics in SimSmith and new features in version 15 of SimSmith. Before I get to that, I'd like to make a couple comments. I've redone my website so that all the videos that I have on SimSmith are available via my website and, of course, via YouTube. You can find the videos at www.w0qe.com/SimSmith, which is also shown below the video here in the comment field. And from there you can look at all the videos. The videos are grouped into two categories: the basic series and another series I called advanced. And this video fits in the advanced category. And thirdly, this video is the first video of a three-part video. The first part is harmonics and new features in version 15 of SimSmith. The second video is about a load generation to be able to apply a predictable various group of load impedances to a circuit in SimSmith. And the third video is the resulting work that I wanted to do, which is to apply a waveform that was rich in harmonics to a filter with various load impedances and calculate the worst case currents and voltages of all the components in the filter so that the filter could be sized to be reliable. This is a project I've done for some people in the past. It's been very laborious to do prior to this version of SimSmith, and I had done it because people had built some products, and it turned out that periodically certain components in filters and stuff were not reliable, and they didn't understand why, and they wanted me to analyze what components they thought were being stressed, etc., etc. The waveform on the screen here shows a fundamental frequency of 10 volts peak that has within it a second harmonic that is 20 dB below the fundamental amplitude, a third harmonic that's 15 dB below the fundamental amplitude, a fourth harmonic that's 25 dB below the fundamental amplitude, and that also shows the resulting signal, which is the blue-green waveform. The blue-green waveform is not that untypical of what you might see on the output of a solid-state amplifier. Now, can we make SimSmith give us this signal, and can we also make SimSmith calculate the results for this type of a waveform? And the answer is we used to not be able to do that, and I don't know of any other Smith chart type programs other than SimSmith that can do it. You can do it in LT Spice, but it's very difficult to do some of the output that I wanted to do. So these three videos tied together here should be kind of an interesting journey into showing what SimSmith is actually capable of doing, and I hope people will find it interesting. The uses for having a waveform with a lot of harmonics in it in SimSmith may be fairly small. There may not be a lot of uses, but the problem that I suggested here is a very good use of it, and consequently, it's nice that SimSmith is capable of doing this. Let's look at a simple SimSmith file here and look at one of the new features in version 15. Previous to version 15, if you clicked on any field, there was a window that popped up here called the View window. And the View window allowed you to see what was in this field. It was nice whenever you had like a file name that was very, very small. The text was very, very small. It's also nice, and I've run into this a couple times, you're capable of putting multiple numbers in a lot of these fields, like the frequency field, the SWR field can have multiple numbers put in it. But if I make a mistake, so if I go here to 14, and let's say these dots right now are 14 megahertz. If I put 14 and I put 16 megahertz in, hit enter, I have 14 and 16 megahertz. This is a nice way to put little markers on the square chart. And if I continue on, I continue putting numbers in here like 18, 20, and then I screw up and hit like a letter W, and then I do 25 and 30 and hit enter. I should get a warning, and I do. This W is not understood by SimSmith. if these values are so small now that I can't see what I'm doing, it's extremely hard for me to edit them. What's now a new feature is I can come up here in this field and I can click here and I can delete the error and then hit enter and be good to go. And that's kind of nice. It may not be a real common thing that people run into, but if you've spent a lot of time putting some specific frequencies in here, I was doing some crystal filter stuff, and the frequencies were all very, very odd. 14.0965, 14.09712, and it was very laborious to re-enter them. It was nice to go and be able to edit the mistake that I had, and I couldn't even see the mistake because the text had gotten so small that there was no amount of me spreading this out that was able to make the text easily discernible. So this is a very nice field. This field is very nice that now it's no longer an output field, but it's also an input field. So enough of that. Let's look at the plot menu here. SimSmith has a few new commands. It's got a command called RMS, it's got one called peak, and it's got one called total power. These kind of replace functions that used to exist, and they can be used in place of those if you want, but they're also necessary for harmonics. So let's look at harmonics briefly. The harmonic command here, by the way, the 2 forward slashes means that the field is commented out, so it doesn't count. There's several ways in SimSmith to comment stuff out, and if you do much plotting, you'll find out that the field over here is only large enough to hold a certain number of things that you can, a certain number of tabs that you're capable of plotting, and after a while they get, like everything else does in SimSmith, it gets too small. So if I want to delete some of these, what I can do is I can either put slashes in front of the line so it doesn't count, or I can do a blanket comment which looks like this, and then it's followed by the same kind of a command. Those 2 commands now are missing from here, but yet they're still in my code. If I want them back again, I can do this. So I can blanket out 20 different lines if I wanted to, and be able to get it back very quickly. So let's look at the harmonic command for a moment. I will enable this one harmonic command here, and what we see is a structure where we say harmonics, parentheses, and then some number of numbers. The number of numbers can be anything you want. I believe it has to be at least 2. The first value is a DC value. The second value is the fundamental frequency. The next value is the second harmonic, third harmonic, fourth, fifth, sixth, seventh, and it goes on as long as you'd like it to go on. When you terminate it, it assumes everything after that is a 0. So in this case, what we've got is we have a fundamental frequency of magnitude 1 and a third harmonic of magnitude 1. Now let's look at that a little more closely, because it's not quite that simple. We have a 10 volt waveform here for our fundamental frequency. It is a 10 volt signal. It's not declared to be an impedance on the output. It doesn't have anything like that. It's just a 10 volt like ideal voltage source, because it's just a number. So what that means is this 10 volt signal here will give me 10 volts here no matter what my load impedance is. So here we see 10 volts. Let's make my load impedance 1 ohm. It's still 10 volts. Let's make it 1 megohm. It's still 10 volts. So that proves it's really a 10 volt signal. 0 ohm output impedance. This is the magnitude specifier. Now, this number is a multiplier on the magnitude. So what this means is we have in the harmonic command, we have a fundamental frequency which is 10 volt RMS times 1. And these numbers down here are complex numbers too. So they can have phase information within them, but the magnitude here is 1. We have a third harmonic which is also magnitude of 1 times this multiplier. So let's look at that. We have a command also called wave. Wave is an oscilloscope looking output. It's kind of funky and it really doesn't belong in SimSmith, but yet it's really nice to have if we're trying to create a waveform. So let's look at that waveform for a moment. If we click on wave here, what we see, and the reason this doesn't show us as a sine wave, I haven't said done yet. If I click done, I now see my harmonic. So let's go back to the other one without the harmonic. We can put a 0 in here for a moment. I'm going slowly with this because this is it took me a little while to figure this out. The bottom line here ought to be time if this was an oscilloscope waveform. Let me get rid of all this other stuff here for a moment. The bottom line should be time here. The independent axis should be time. The vertical axis is, of course, whatever you want to plot it as. When we plotted it against the y, plotted against the y2 axis with a label of V up here for volts, and we can see that our waveform is a sine wave. It goes from an amplitude of basically 14.14 volts, which is a 10 volt RMS waveform, which is what we expect. And SimSmith shows us 2 cycles, exactly 2 cycles of the fundamental frequency. Ignore the bottom line here. Matter of fact, we do not even need to have sweep turned on, and we still see the waveform. All the other functions need to have a sweep turned on to work, but the wave function does not. So here we have this wave function. It shows us our fundamental frequency. Now, if we come and notice it starts at 0 here and has phase of 0. It's a sine wave, starts at 0 and starts rising immediately. We go back here and we make our third harmonic. We get rid of our fundamental, which is something that's kind of interesting we can do here. We can get rid of our fundamental, have just the third harmonic. Say done. Now we have again another waveform that's our third harmonic. It's 3 times, so we have 6 cycles here in this waveform, and it starts again with a 0 degree phase angle. We can make it start with a different phase angle by, let's put a -1 here. That'll be a 180 degree phase angle. Starts off this way. We can do several other things. We could give it a minus J. If we give it a minus J, it'll have a -90 degree phase angle when it starts. Now, if we combine that with our fundamental frequency, we have a fundamental which is a magnitude 1 at 0 degrees. We have a third harmonic which is a magnitude 1 at -90 degrees, and that's the resulting waveform. We can also do some things along the lines of putting a number in here. Let's put a number in here that's maybe like, how about 0.5 plus 0.5 times J. That will be a waveform which has magnitude 0.707, and it'll be at 45 degree phase angle. Let's look at that one by itself real quickly, just to be sure we got that right. Whoops. Now we see a waveform that starts at 45 degrees, and it is a magnitude 10 volts peak, which is what you would get with a 0.707 volt RMS, with a 7.07 volt RMS signal. Remember, it's 10 volts times the magnitude of this, which is 0.707. Fortunately, everything is not quite that complicated. In a normal amplifier that you had harmonics, you would have this harmonic would be, the fundamental would be at 0 degrees, just because it doesn't matter where the fundamental is. And the third harmonic is actually in phase with it. So it might be a waveform that looks like maybe something like, say it's a quarter of the amplitude. We'd have a waveform that might look like that. For different examples here, real quickly, let me bring this up. Here's something that was done in LT Spice a while back. But it shows this command here, fundamental and third harmonic equal amplitude, both at 0 degree phase angle. The light brown is the fundamental, the dark brown is the third harmonic, and the green is the resulting waveform. Notice how much different the green waveform looks in all these cases, yet all the cases have exactly the same harmonic amplitude relative to the fundamental. And it's just, this is just a quick aside, but SimSmith is extremely flexible in this way. As is typical in SimSmith, when you get some of these features, you get a little bit more than you need. And so when I asked for harmonics, I didn't really realize what I was asking for initially. And I got harmonics where the amplitude was adjustable and the phase was adjustable. In reality, that's really what you want. But so it seems a little bit complicated sometimes to do. So we have this waveform now, which has an amplitude, fundamental amplitude of 1. And for ease of doing this, let's just make this 0.5 now. It's a little bit larger. Whoops, a little bit larger signal. It's half amplitude on the third harmonic. There's our waveform. We can look at things now like the RMS value of that waveform. So we execute a command, RMS. This is the label we're going to have. It's RMS v, L.V, which is right there. This is what we're looking at, L.V, capital V. Capital V means on a... Let me do a real quick review here. If we had a component like this, and we did L1.V, capital V, we'd be looking at the voltage right on this side from here to ground. If we did L1.small v, we'd be looking at the voltage across this component. So in the case here, we could look at L.capital V or L.small v. They both give you the same answer because the voltage across the component is the same as the voltage to ground. So back here again. So what we've got now are these commands. Let's look at the RMS value of this waveform. It turns out it's 11.18 volts. It's kind of nice to be able to measure that. We can look at the peak value of the waveform. The peak value of the waveform is 15.214. And then we can look at the power. Now, power is an interesting thing, and there was an error in previous versions of SimSmith previous to version 15. They didn't calculate the power correctly with harmonics. Version 15 has that done correctly. If we look at the old way of doing power by just clicking here, we get an answer of 2 watts. We had a 10 volt RMS signal in the fundamental. We had some harmonic power in here, which you would think would give you more power. 10 volt RMS signal here, squared is 100, divided by 50 ohms is 2 watts. The old way of measuring power with the plot command, like this command, or clicking right here is exactly executes this command right here. We can prove that very easily. 2 watts again. It's not, they're not right in the case of harmonics. Neither is the voltages done by the plot command here. If we look, we'll get that in a second. Let's look at the power real quickly though to begin to finish this up. If we look at the new way of calculating power with the total power command here, what we see is 2.5 watts. This makes sense. Superposition applies in a situation like this. We have a linear time invariant circuit. We have a 2 watt fundamental. We have a 10 volt fundamental signal which produces 2 watts into the load. We have a third harmonic which is 5 volts. The 5 volt signal produces a 5 squared divided by 50, a half watt signal into the load. The 2 watt signal from the fundamental frequency and the half watt signal from the third harmonic produce a 2.5 watt signal, which is accurately measured with the total power command. What this means is you can use RMS, peak, and total power for all applications, whether there's a harmonic present or not. If we get rid of our harmonics here, these commands still work. Again, 2 watt output, which is what we expected. A peak value of 14.14 volts. RMS value of 10. Exactly what we expected. So, kind of a unintended consequence of these new features is that these new features allow you to replace the old ones. Now, why would we want to replace the old ones? Well, in the case of power, you want all the power to be included if you're looking for a component to be sized. So you don't want to use the old power. You might want to look at just the fundamental piece that gets through. You can do that with looking at the old way. But in the case of voltages, even though the power is the same on the output, no matter what the phase is, the voltage on the component is not. We saw that on the previous graph, and we can see it again right here. If the harmonic's full size, this gives me a peak voltage of 21.7 volts, 21.8 volts. If the phase is like this, we now get a peak value of 28 volts, even though the RMS value is the same in all cases. It's 14 volts there. It's 14 volts there. It doesn't change. Yeah, I'll do one more here. And it's 14 volts there. The peak value keeps changing. The RMS value stays the same. Let's do one more quick example here. And that is, let's get rid of this harmonic command and replace it with this one. You might not recognize this command, but basically it's a fundamental frequency. The third harmonic is of 1/3 amplitude, fifth harmonic is of 1/5 amplitude, seventh harmonic is of 1/7 amplitude. The even harmonics are all gone. And the resulting waveform, if we do this, is, gotta wait a minute, almost a square wave. This is basically the way to generate a square wave. Interesting to notice that we've included 25 harmonics and we still do not have a perfect square wave. I don't know how many harmonics you need to include. Wikipedia has, I think, at least they used to have a very interesting little visual graph that you could include as many harmonics as you wanted and see the result. And you needed to include about 50 harmonics before the square wave really got to be good. But nevertheless, SimSmith does do these kinds of calculations, which is extremely convenient. Now, at this point in time, I had a real concern about, well, I've got a fundamental and I've got harmonics, but how does sweep apply? So we need to look at another example real quickly to see how sweep applies. Now here's a new graph. It's similar to the last one, but what I included in this graph is a parallel LC circuit, which is resonant at 42 megahertz. 42 megahertz is the third harmonic of 14. What this means is the signal here, which has the fundamental and a harmonic both in it, will have the 42 megahertz signal removed from here. So let's plot. So this is the waveform. So let's look at what we've got again to start with. We've got a very large harmonic, third harmonic equal to the fundamental. And we plotted the waveform. This is exactly what we'd expect to see. We plot the waveform at L right here. What we see is just the fundamental, which indicates that the filter has done exactly its job. Now, I don't think there's any question that this is what we expected to see. However, if we sweep the frequency, which we are doing right here, the waveform doesn't show any. Remember, the waveform is kind of independent of sweeping. But these commands here are not independent of sweeping. So let's get rid of these two commands, and let's look at the RMS value right here. That's RMS LC1.V. We'd expect that to be a constant voltage, and it is. It's a 10 volt. It's a 10 volt RMS signal at 14 megahertz, and it's a 10 volt RMS signal at 42 megahertz in the non-swept case. But in the swept case, let's pick right here. At this point right here, this is a 30 megahertz 10 volt signal and a 90 megahertz 10 volt signal. And we can see that by looking at the power in the output. Let's look at the power in the output here, the total power. Oops, I'm sorry. That's what I wanted to look at. Now I'm looking at the RMS value at the load. The RMS value at the load shows two places where the RMS voltage drops. So this place right here, it drops, is because we have this is indicating the fundamental frequency up here. So a fundamental frequency of 14 megahertz with an equal amplitude 42 megahertz third harmonic. The third harmonic gets sucked out of this filter. So our 10 volt signal plus our 10 volt harmonic gave us a 14 volt RMS signal. This 14 volt RMS signal gets dropped back to 10 volts here. 10 volts. I'm not quite on the dot exactly. The way I've got the number of points set, but it's basically 10 volts here. But I also see another one up here. And what's going on up here? Well, up here I have a 42 megahertz fundamental frequency and a 126 megahertz third harmonic. Well, this filter still works, so it traps, instead of the harmonic, it's trapping the fundamental frequency. So what we do when we create this harmonic command, it applies to exactly what the generator is doing. So if the generator is being swept, the harmonics are being swept too. So at a place at like 20 megahertz, we'd have a 20 megahertz fundamental, a 60 megahertz third harmonic. So it tracks everywhere. I don't know that that's needed in this example, but that's how the harmonic command works. And it's kind of interesting. It's just, I'm trying to show how it works, not necessarily, a reason for it working that way. Another small item that's kind of a small problem is if our voltage source here was defined to be an X match, you would normally not expect the harmonic to be matched to the circuit and the fundamental. Right now they both match. That generally is not a problem, but it's probably not right. And Ward is aware of that. I don't know if something will change or not. I've never had a problem because generally when I face a filter or something with a lot of impedances, I don't have a generator that the X-match command is appropriate for. I expect the power to drop due to mismatch loss, and X-match stops that from happening. Anyways, I hope this has been an interesting journey along how harmonics work in SimSmith, and the next video will have nothing to do with this video, but it will have to do with the other end. So we dealt with the generator end. The next video is going to deal with the load end, and then the third video is going to deal with tying them together with a different filter in the middle. So hopefully this has been interesting. I'd like to encourage those people who have not subscribed to my channel to please do. That's the only way I kind of know really how many people are actually interested. I do get emails periodically from a few people, and I get a few comments. But if people enjoy these videos, I'd appreciate I'd kind of like to know about it. It's hard to gauge how much activity there is in the community. I can see the total number of views of the videos. They're not very high compared to like if I made a cat video on a Roomba or something like that. I'd have tens of thousands of views easily. But I think it's kind of important to be able to document how SimSmith works. It's a very competent program. But with the competency of the program comes a degree of complexity that's a lot easier to explain in a video than it is, in text. Thank you again.